Hello, I'm Karen Daniels from the Physics Department at North Carolina State University, and I'll be talking to you today about why we should be studying granular materials under varying degrees of gravity. I'm primarily a laboratory scientist interested in the mechanics of soft materials, so when I first heard about rubble pile asteroids such as Bennu, shown rotating at right, I was intrigued at how there came to be a stable spinning pile of grains in space. As we send missions to photograph and explore planetary bodies, planetary scientists will be investigating what forces sculpted different surfaces and shapes throughout the solar system. And this will lead us to a better understanding of the history of our solar system. So granular materials are present throughout the solar system. My colleague Paul Burns shared with me the image shown here of the surface of Mars. And one of the things you can see is the tracks left by rolling boulders against the surface of granular regolith. So better knowledge about the mechanics of granular materials under lower gravity than we experience here on Earth would help guide us in using remote images such as these to infer material properties of the underlying surface. As we send crewed and robotic missions to the surfaces of planetary bodies, their explorations will need to perform functions such as digging and anchoring, building, transporting materials, and locomoting. We already know from the successful Mars rover missions that they had difficulty maneuvering in loose sand, an example of which is shown at the right. So how does this happen? So state-of-the-art granular materials have been primarily built to explain our experiences here on Earth in 1G, and they don't necessarily work in these new contexts. Of course, humans have thousands of years of engineering experience using granular materials to build stable structures. We also have experience in digging and compacting, materials handling, and so forth. However, we remain novices on any other circumstances besides those of 1G. So what changes as we lower gravity that makes it harder to extend our existing knowledge into these new contexts? The first important difference is whether van der Waals forces played a significant role in the dynamics of the granular material. So van der Waals forces are intermolecular forces that on Earth are only important for extremely fine powders. They're basically molecule-molecule interactions. However, the work of Sanchez and Shiras has used observations of rotating asteroids to show that such bodies have a non-zero finite tensile strength. They estimate the strength to be about 10 kilopascals, so that's about the tensile strength of a ripe tomato. This is actually not something that we have experiments on, however. And so we need to quantify and understand how these van der Waals effects arise in microgravity using experiments on real materials. So rubble pile asteroids, which I started my talk with, are small and light. They're perhaps 50% porous and therefore have very little surface gravity. For Bennu, which I'm using this example here, this gives rise to an escape velocity that is so slow that its speed is approximately that of a falling feather here on Earth, right? Even I, with a not very good softball arm, can throw something at that speed. As such, any interaction with the surface of a rubble pile asteroid can easily have catastrophic consequences. We know that sound propagation in granular materials is highly nonlinear. Simulations done by Gomez et al. Have shown that when they are loosely packed, they're barely rigid and have a vanishingly small speed of sound. As such, even minute mechanical perturbations will propagate as shocks, as seen in the images at right. Again, these have been done in simulations, and microgravity experiments are needed to quantify and investigate such phenomena. And we anticipate this will give rise to both new physics and to an understanding of the implications for the performance of practical tasks on low-gravity surfaces. So we have two challenges in order to safely explore. I think of these as leave no trace, which is the key principle of outdoor exploration here on Earth, along with safety first. Okay? As some examples, when the TAG-SAM sample collection on Bennu, or the bouncing of Rosetta, or the wheels of the Mars rovers occurred, these are all examples of challenges faced in achieving these safe explorations. Okay? So one of the key issues that granular scientists should tackle is the hierarchy of speeds. We have the speed of the probe or the digger or the wheel, the speed of sound, the escape velocity on that surface, And I'm particularly interested in what dynamics occur when these speeds are similar in magnitude. So as an example, we're going to look at the problem of how far into the surface a robotic arm or an instrument might penetrate. And I'll explore this question using a sample microgravity experiment done by researchers in my lab that was funded through NASA's Space Tech Ready program. This project allowed us to perform experiments in Martian, lunar, and microgravity during a parabolic flight campaign, shown here, followed up by experiments back in our labs on Earth. It has educated half a dozen undergraduate students in the science and technology of both granular materials and microgravity experiments. So during our flight campaigns, we performed experiments to insert a flexible probe into a model surface made of photoelastic grains. These are grains which are bright when they're carrying more force. And what you'll be able to see as the movies progress is, even without going into the quantitative analysis that's found in the preprint listed at the bottom, the pattern of force transmission is dramatically different in Mars gravity versus microgravity. Okay, the lower the gravity, the more the grains behave reliably like a fluid without the accompanying stick-slip behavior that we're accustomed to in higher gravities. So what comes next in the coming decade? Experiments at a range of gravitational accelerations are going to be key to understanding granular dynamics, and this will enable us to discover new phenomena, develop realistic models. These in turn will improve our interpretation of planetary geomorphology and create safe conditions for in-situ resource utilization as we explore our solar system. And if you want to hear more from me, you can find me on Twitter at Karen E. Daniels. Thanks.